So our next speaker is Samuel Olivier from the University of California, Berkeley. His field is nuclear engineering, and he has done practicums at Los Alamos as well as Lawrence Livermore National Lab.
Thank you. Yes, my name is Sam Olivier. I'll be talking about high-order moment methods for thermal radiative transfer. And this work was performed at University of California, Berkeley. I graduated, and I'll be starting as a postdoc at LANL in 3 weeks. So on to motivation. So why did I do this work? The key is that numerical thermal radiative transfer is crucial for inertial confinement fusion. So thermal radiative transfer describes the conservation and transfer of energy between photons and matter. It's a dominant form of heat transfer in the conditions of ICF. And so modeling ICF requires the simultaneous modeling of plasma physics and thermal radiative transfer. So I'm showing National Ignition Facility. It's at Lawrence Livermore National Lab. And inside of this dome, this target chamber is the Hall ROM. And inside of the Hall ROM, there is isotopes of hydrogen. The world's largest laser comes in and heats up this Hall ROM, the walls of the cylinder, to high temperatures. And the goal of this talk is to develop efficient numerical methods to trace the radiative heat transfer from the walls into the fuel. And in codes of the National Ignition Facility, TRT is typically the bottleneck. It can be 90% of the runtime and memory. Existing codes are extremely optimized, so we need algorithmic improvements. The trouble is that solving thermal radiative transfer is very difficult. The equations have a large phase space, and they have significant nonlinearity. So these two equations are the equations of thermal radiative transfer. We have a kinetic equation. It's a Boltzmann transport equation. It has a very large phase space, 7 dimensions. So corresponding to a photon is located in 3-dimensional space. It has 2-dimensional direction, 1-dimensional frequency, and then it's located in time as well. And the radiation field is coupled to the material through the emission term. So this Planck emission term, matter emits radiation at any temperature, and in the temperatures of ICF, photons are emitted in the soft X-ray regime. And here we model the material temperature, so it gains energy by absorbing radiation and decreases energy by emitting radiation. And this Planck term B is very nonlinear, so it makes the problem difficult. But fortunately, this nonlinear physics occurs under integrals. So here we're integrating out the direction variable and the frequency variable. And these integrals are called moments. So this motivates the use of moment methods, which are the title of this talk. So for some context, we're interested in high-order methods on curved meshes. And this is because Lawrence Livermore's next generation code to model the National Ignition Facility is based around these techniques. And so at the bottom, I'm showing a high-order Lagrangian simulation where the mesh deforms with the materials. So as the materials deform, the mesh moves with it. And we end up with these distorted interfaces. And the goal is to be able to solve thermal radiative transfer on a mesh like this. So the default approach would be to take the high-order element and then convert it to a low-order refined version. So we're approximating it as straight-edged. But the issue is that this might take more than 1 or 2 refinements, and this will drastically increase the simulation cost. And also there's a robustness issue. If the mesh is very distorted, refining it can lead to ill-defined meshes. So we want to avoid the lower refined and solve directly on the high-order mesh. So now moment methods, that's the title of this talk. They couple the kinetics of that high-dimensional kinetic equation to a lower dimensional model in order to form efficient iterative algorithms. And so some background, the moment equations, it's a system of partial differential equations that describe those integrals I mentioned directly. They have a lower dimensionality, so they're cheaper to solve. But due to that, they require closures in order to get the physics correct. And so the moment methods use a bidirectional coupling. This high-dimensional kinetic equation informs the lower dimensional model through these closures. But then the moments, so the lower dimensional model is used to compute the expensive physics in the higher dimensional model. And the crux of this research problem is that the closed moment equations have an unusual mathematical structure. So they're difficult to discretize and solve. And this is true even for low-order methods. So now on to the moment methods used in radiation transport. I'll first simplify the problem. So we'll neglect time and frequency dependence and replace temperature coupling with isotropic scattering. This is a common proxy in my field. So we end up with a simpler equation where it has streaming, collision, scattering, and source terms. And this is an integral differential equation that describes the balance of photons. And in this angular variable, this direction of flight variable, we'll use something called discrete ordinance, which collocates at discrete angles chosen from an angular quadrature rule. And then in spatial variable, we'll use discontinuous Galarkin. And the key to this proxy is that we still have this moment-based physics. The scattering term is based on the 0th moment of the kinetic solution. So now I'll derive the moment equations, and the problem is that they always have more unknowns than equations. So in the top right, I have the kinetic equation, the transport equation, and if we integrate over all angles, we get the 0th moment. And if we first multiply by the angular variable and then integrate, we get the first moment. And this is all just definitions. I'm just defining this phi to be the 0th moment, j to be the first moment, and p to be the second moment, with these q's are just moments of the fixed source over here. And so now we see that we have a scalar, a vector, and a symmetric tensor as unknowns, but we only have a scalar and a vector equation. So we need to provide an auxiliary set of equations that define the second moment in terms of the lower moments. And so I'll present on two methods. The first uses a multiplicative closure. So we say that the second moment is equal to this Eddington tensor times the 0th moment. And this Eddington tensor is dependent on the kinetic solution. So this happens to be the ratio of the second moment to the 0th moment. And this is just an algebraic reformulation. We've just multiplied and divided by the same thing in order to create a closure. And alternatively, we can use something called the second moment method, which uses an additive closure here. So in the same way that we multiplied and divided, here we're adding and subtracting the same term. And so efficient algorithms are found by iteratively solving the transport equation with the moment equation. So the top line is the transport equation for both methods, but then the lower line is the moment equations with the certain closures. So VF uses the multiplicative closure, while the second moment method uses the additive closure. And so now we're solving for both the kinetic solution, psi, and also the moment equation. So we've added unknowns, but the key is that the closures are weak functions of the solution, so we can actually design iterative schemes that have rapid convergence. And such an iterative scheme is to lag the scattering source, solve for the psi variable, the kinetic solution, compute the closures. We can then solve the moment equations and get a new scattering source, and then we'll repeat this process. And the same is true for second moment method, except the closure is now different. It's the additive closure, and same iteration though. And these arrows here between the moment or the kinetic equation and the moment equations are computed with finite element interpolation and discrete ordinance angular quadrature. And this is a good place to see the key differences between the two methods. One, VF, this closure is on the left-hand side. It modifies the properties of the partial differential equation, whereas for second moment method, the closure is on the right-hand side, and it appears as a source term. And so the goal of this work is to implement these algorithms and then compare their iterative efficiency and see whether the placement of these closures is an important factor. So like I mentioned, the key difficulty is that standard discretization techniques do not directly apply to the moment equations. And so I'm showing the VF equations on the top right, and if we solve for J and plug it into this first equation, we would get the second order differential term. And if we expand this product, this E times phi, we would get terms that look like diffusion, advection, and reaction. But the issue is that closures are generally not differentiable. So this Eddington tensor is generally not differentiable. And this is because the kinetic solution itself can be discontinuous. And we're also using numerical approximations that are discontinuous. So we can't do this simplified process of writing it in a standard form. And we instead have to develop specialized discretizations to handle this term. So on to the discretizations that I came up with. My approach was to first start with the VF moment system and discretize it in a way that we can leverage existing solvers. And this deviates from the historical approach where the key or the design, they were designed to match. So the kinetic discretization and the moment discretization were designed to be the same. So we're deviating from that. We're allowing them to be different. And this is supported by a paper from 2018 where it showed that you can choose those discretizations differently and you'd still get the same convergence. And so our hypothesis is that if we design the discretization properly, we could leverage what's already out there. And then the second step is to take any of those VF methods I'll present later. We can convert them to second moment methods just by leveraging the close connection between their closures. So I'll go through, the first method uses discontinuous Galarkin techniques. So the VF moment system was discretized with discontinuous Galarkin by extending the framework developed for the model elliptic problem. So there's a famous paper that's unified analysis of DG methods for elliptic problems. It develops a systematic process for discretizing the standard elliptic problem with its discontinuous approximation. So here we're allowing the solution to be discontinuous at element interfaces. And so I extended this paper to the VF system by walking through it line by line and carrying over the differences. And that led to a framework of discontinuous Galarkin methods. And I also extended this, my collaborators and I proved that this uniform subspace correction preconditioner, so we can solve the resulting system, and we proved that we could do that every time. So I don't have time to explain how this works, but I've included a paper link, so you can find that on arXiv. So next, we derive this framework. We can extract a continuous method from this just by swapping out the approximation space. So if we take the discontinuous space and just replace it with a continuous one, we actually get a new discretization. And this is effectively preconditioned by algebraic multigrid. And here I'm just saying that on the implementation side, we can just take the equations we formed last time and just assemble it to get a new discretization. And then so my third method is based on mixed finite elements, and here the difficulty is that the closure alters the requirements of the approximation space. So if you were to go through and discretize these equations, you'd have these two conditions that one, the solution has to be continuous, the normal component has to be continuous across mesh interfaces, and the other is that this E times N has to be continuous. So this diagram here just shows that when you apply the adjuvant tensor to the normal, it induces a rotation. And so this is a new requirement. And the trouble is that there's robust methods invented for this requirement, but there's no techniques available for this arbitrary component. So this means I had to use DG-like numerical fluxes, and this is demonstrated in this paper I've linked below. And I found a way to solve this via mixed finite element hybridization and algebraic multigrid. And then so finally, any of those methods I just presented, if we just take this E times phi and replace it, so this is the VF closure, the multiplicative closure. If we just replace it with the additive closure, we can algebraically convert any VF method to be a second moment method. And the key here is that since the source term is the closure, the left-hand side is a standard elliptic partial differential equation, and we can immediately apply any preconditioned iterative solvers. So on to numerical results. I have a well-designed method of manufactured solutions problem to show that we get second, third, and fourth order accuracy for linear, quadratic, and cubic finite element interpolation. And if we zoom in, we can see that the discontinuous Galarkin and the continuous finite element methods have similar error behavior, whereas the mixed finite element-based methods all have similar behavior. And this is all on a high order third order curved mesh, so refinements on a third order mesh. So next I'll show on the crooked pipe. So this is a more realistic multi-material problem. And radiation streams in on the left-hand side, and it goes through this yellow region, and it scatters in the blue region. And this is a difficult problem because there's 1,000 times difference in material parameters between these two materials. And we'll test this by refining this problem in H and then also in the polynomial order. So this is a big table of numbers about convergence of the moment algorithm. And so we're refining in the mesh size and also in the polynomial order. So we'll first look at the first polynomial order, and we see that all the methods don't scale that much with H. And also between methods, they're very similar, with the second moment method being slightly slower in most cases. And this is true for all the polynomial orders. And if we compare least refined to most refined, we see there is some increase, and this is mostly due to the polynomial order being increased. So next, this is the precondition of iterative solvers. So we have the discrete moment system, and we need to be able to solve that with something like conjugate gradient or biconjugate gradient. And so each of these methods were refined, and then also in polynomial order, we see that going from the least refined to the most refined, there's very mild increases. So this means that the inner solvers are scalable in both the mesh size and the polynomial order. And then finally, I repeated that in parallel. So this test is a 32 times increase in number of unknowns. So this is out to over 1 million elements with 1,000 processors. And we see that all the methods are efficiently solvable even on a much bigger problem. So on to conclusions. The big conclusion for my dissertation was that moment systems can be effectively discretized using the approach I laid out, so we can start from methods that can be solved on standard problems and move them to the moment system. And also the very exciting result is that the moment methods are insensitive to the choice of both the system's closure and its discretization. And so these claims are supported by my results. I had 2 closures, 3 discretizations, and they all exhibited similar accuracy, efficiency, and robustness on a challenging proxy problem from thermal radiative transfer. And so this means that the moment methods are insensitive to these parameters, so we have the flexibility to design it for computational efficiency and multi-physics compatibility. And the big impact of my work is that both Lawrence Livermore and Los Alamos are currently working on implementing these in production algorithms, so there's a possibility that it'll be run on an exascale machine. So I have some references, the software I used, and I wanted to say thank you for being here, and to CSGF, thank you for supporting me. And if you're interested in my work, you can find my website, has my papers. Thank you.